Now we'll be talking about superposition. This is basically a linear circuit concept. It assumes that the circuit is linear. Now, in superposition, the idea is that if you have multiple sources, it can be uh, dependent or independent sources. So if you have those sources, let's say, for example, in this circuit, we have an independent current source and we have an independent voltage source, and we have to find out the voltage V0 across the 6 kilo ohms resistance. Now, the idea is that if the circuit is linear, V0 will be the summation of the individual contribution from this 3-volt source and then this 2 milliampere current source. So if you solve for the circuit and calculate V0 by assuming only 2 milliamperes supplying the current or voltage and add them up with the, the current and voltage supplied by the 3 volt, the result will be the same as the original circuit, as you can see here. So in order to do so, we first take the contribution from, since we have here two independent sources, so we have to solve the circuit two times, one for the current source, one for the voltage source. So the idea is that this V0 can be calculated from these two equivalent circuits, where in one circuit we are assuming the current source is turned on while the voltage source is turned off. And when you are assuming the voltage source to be turned off, since this will become 0 volt means short circuit, so therefore the equivalent of the 0 volt source is just a straight line of wire. And from this circuit we'll find the contribution of V naught from 2 milliampere source only. And then we have another circuit where we turned off the current source, and since we turned off the current source, that means the current through this branch will be 0 ampere, and for 0 ampere it is replaced by a open circuit. So we see that this circuit branch is completely neglected. So now we have one circuit from where the contribution will only be from the current source, and another circuit where the contribution will only be from the voltage source. Now from here is just we can apply current divider rule, find out I naught, and if you want to find out I naught, we multiply by the 6 kilo ohms to find out the V naught prime, which is the contribution from the current source only. And in the second circuit, it's a series circuit, so we apply voltage divider rule to find out V naught prime. And once we find that up, we can find the original V naught by summing the V naught prime from the current source and V naught double prime from the voltage source to get the ultimate V naught, which is 6 volts in this case. So that's the idea of superposition. So in this example, we see that you have to use linearity to find out I naught, assuming that I naught is 1 milliampere. So what you are assuming is that, okay, I want to find I naught, but I start with by assuming that I naught is 1 milliampere. So you assume that 1 milliampere flows in this branch, and then you track back to find out what should be the source of the current, what should be the value of the current source for which you will have 1 milliampere flowing through this branch. Now once you find that, you take the ratio of the current sources to find out the actual current flowing in this branch. All right, so let's see it in an example. So since we assume that 1 milliampere flows through the 4 kilo ohms, so what should be the voltage across the 4 kilo ohms? It should be 4 volts, right? So now since this is 4 volts and this 4 kilo ohm and 4 kilo ohm resistance is in parallel with this 2 kilo ohm plus 2 kilo ohm branch, right? This branch. So this is in parallel with this 2 kilo ohm plus 2 kilo ohm branch. So we can say that the voltage across the 2 kilo ohm plus 2 kilo ohm branch is also 4 volts, right? So since we have 4 volt across 4 kilo ohms, which is this 2 kilo ohm and this 2 kilo ohm, so the current flowing in this branch is also 4 volt divided by 4 kilo ohm is 1 milliampere, right? So we have 1 milliampere current flowing in this branch, and we assume that 1 milliampere is current is flowing in this branch. Now, since this 4 kilo ohm is in parallel with again with this 2 kilo ohms, so we know that the voltage across this 2 kilo ohm is also 4 volt. If the voltage across this 2 kilo ohm is also 4 volt, then the current in this branch is 4 volts divided by 2 kilo ohms is 2 milliampere. So now we have three currents, one current going down 2 milliamperes, right, which is this one, another current going 1 milliampere through these 4 kilo ohms, and another current 1 milliampere going into the rightmost branch. So in addition, so in net, we know that the total current going into the through the 2 kilo ohm is basically 2 milliampere plus 1 milliampere plus 1 milliampere, which is 4 milliampere. Now, if 4 milliampere current flows through the 2 kilo ohms, so we know the voltage across the voltage drop across the 2 kilo ohms would now be 8 volt, right? It should be 8 volt, right? Now we know that 12 milliampere, so now we know that 4 milliampere flows into this 2 kilo ohm branch, and we know the voltage across the 2 kilo ohm is 8 volt, and we know that the voltage across this 2 kilo ohm is 4 volt, right? Now, if you apply KVL in if you apply KVL across in this loop, right, then you can find out the voltage drop across 2 kilo ohms. So now if you apply KVL, so I assume that the current is coming downwards. So this should be plus, this should be minus. So if I apply KVL, so this V, let me call it V1. All right. So what should be my V1? It's minus V1. Yeah, I'm going clockwise. Then it's plus 8, right? Then it's plus 4 is equal to 0, right? So my V1 should be 12 volt, right? My V1 is 12 volts. Now if V1 is 12 volts, what should be the current going through these 2 kilo ohms? It should be 6 milliampere, right? So the current going through this 2 kilo ohm is 6 milliampere. Now we have 4 milliampere current going on the right, 6 milliampere coming down. So I should have 10 milliampere coming from this source, right? So I should have 10 milliampere coming from the source if I assume I naught to be 1 milliampere. But my actual source is 12 milliampere, right? So that means actual source is 1.2 times higher than what I am getting, right? So that means my I naught should be 1.2 times than 1 milliampere. So my I naught should be 1.2 milliampere because originally I took it to be 1 milliampere. Now here we see another example where we have two independent sources, one independent voltage source and one independent current source, right? Now, when we apply superposition, for at first what we do is that we find out the contribution from this 2 milliampere current source. So we turn off this voltage source, and turning it off means it is a short circuit, and the equivalent circuit is this one. We have to find I naught, right? And now since we have to find I naught, what we do right now is that we see that this this 6 kilo is in parallel with this 2 kilo ohms, which is in series with this 3 kilo ohms, right? So the equivalent left hand side resistance is 4.5 kilo ohms, which is in parallel with this 3 kilo. So at first we have to find out what is the current going on the left hand side, what is the amount of net current going on the left hand side, right? So that's why we took this equivalent resistance of 4.5 kilo ohms, and from this equivalent circuit we do the current divider rule to find out the current going into the left hand side to be 0.8 milliampere. So this is the current going on the left hand side, and this is being split into 6 kilo ohms, right? And I naught or between 2 kilo ohms. So again here at this node we will have current divider applying. So when we apply current divider rule between 2 kilo ohms and 6 kilo ohms with 0.8 milliampere going on the left, we find that I naught prime should be 0.6 milliampere for the 2 milliampere current source only. For this 2 milliampere current source, the contribution to I naught is 0.6 milliampere. Now next we turn off the current source, right? We turn off the current source. That means this current source will be now a open circuit, as you can see here, and we have to find out I naught contribution only from the 6-volt source, right? And the equivalent circuit is shown here. So here what we do is that you see we apply a source transformation here, as we have seen earlier. Since the 6-volt source is in series with the 6 kilo ohms, we can apply a source transformation and convert it into an equivalent current source, where the current source magnitude is 6 volts divided by 6 kilo ohm, which is 1 milliampere, and this should be in parallel with the 6 kilo ohm resistance, which was in series with the voltage source. So that 6 kilo ohm source is in parallel. Now we have another 3 kilo ohm and 3 kilo ohm in series, so we have another 6 kilo ohm source was a resistance in parallel, right? So these 6 kilo ohms and these 6 kilo ohms, which should these 6 kilo ohms should be in parallel, right? Should be in parallel with the current source. If you do the source transformation, so it should be something like this. You have the current source and it should become 6 kilo ohms like this, right? Now remember you have 2 kilo ohm coming down, and you have another 3 kilo ohm plus 3 kilo ohm, another 6 kilo ohm. So these 6 kilo ohms and these 6 kilo ohms are in parallel, right? All these three resistances are in parallel. So we combine these two 6 kilo ohm resistance, we combine them into an equivalent resistance of 3 kilo ohms, see, because they're in parallel, and this is the net equivalent circuit. Now what should be the contribution of I naught prime? So this 1 milliampere will be divided between these two branches. So we use current divider rule and find out that I naught double prime is basically 0.6 milliampere. So what should be my net I naught? I naught should be 0.6 milliampere, which is from the voltage source summed up with the another 0.6 milliampere, which is coming from the current source, and the net current is basically 1.2 milliampere. Now we have another circuit. Here you see that we have three independent sources, right? So now we have to solve the circuit three times, one for each of the sources. So when we turn off the voltage source, it is a short circuit. When you turn off the current source, it is an open circuit, right? So we start with by finding the V naught contribution from this 6-volt source only. So we turn off the 12-volt source, it becomes a short circuit. We turn off this current source, which becomes an open circuit, and the equivalent circuit is shown here, right? Now, you can see, if you see closely, this 6 kilo ohm resistance is in parallel with this 6 kilo ohm resistance, because they share one node here and they share a common node here. So they are in parallel, right? So this becomes 3 kilo ohms resistance, which is in series with this 6 kilo ohm resistance, and these 3 and 6 kilo ohm resistance are in parallel with this 6-volt source, right? So now basically the equivalent circuit becomes basically something like this. We have a 3 kilo ohms in series with the 6 kilo ohms, right? And they are in parallel with this 6-volt source, right? And then the circuit continues. This 6 kilo ohm and this 6 kilo ohm, this 6 kilo ohm circuit continues at the bottom, right? But since this 6 volt is in parallel with the 3 kilo ohm and the 6 kilo ohm, which are in series, I can apply KVL there, the voltage divider, and find out the contribution of the 6 volt source to this V naught prime, and this becomes basically minus 2 volt. Now why it is minus? Because you see the polarity of the sign of the voltage source, right? It is positive at the bottom, it is positive at the bottom, but this is opposite to the polarity of V naught. So that's why the negative sign appears for this contribution. Now to find out the 12-volt source contribution to this V naught, we turn off this voltage source, it becomes a short circuit, and we turn off this current source, which becomes an open circuit, and the equivalent circuit is shown here, right? Similar to this one, if you see that similar to the previous circuit, this 6 kilo ohms is in parallel with this 6 kilo ohm because they share one node here and they share another node here. So these two resistances are in parallel. So it becomes a 3 kilo ohm resistance in series with this 6 kilo ohm resistance. And they are in parallel with this 12 volt source, right? So now we apply another voltage divider to find out the contribution to be 4 volt. And now there is no negative polarity because the plus of the voltage source and the plus of the V naught are in the same direction. So therefore, there is no opposite polarity. Now for the last step, we want to find out the current contribution, the voltage contribution from this independent current source. So for that, we turn off the voltage source, it becomes a short circuit. Turn off this voltage source, it becomes a short circuit. Then the next equivalent circuit is this one, right? The next equivalent circuit is this one. Now what we do is that since this is a current source, right, and this is a voltage source, right, and this is a current source and these are these resistances, right? So now these resistances are of equal magnitude, if you can see here, all are 6 kilo ohms, right? So what you can do is that you can split the current equivalently into the three branches, right? So since this is 6 milliampere, it will be divided into 2 milliampere to the left, 2 milliampere at the top, 2 milliampere on the 2 milliampere on the right, because the resistances are equal. And if you have that 2 milliampere, you can multiply with the 6 kilo ohms to get 12 volt. But in this case, it will be minus 12 volt because the current is entering the negative terminal. Now, this is one way of seeing it. The other way is that you can combine these three resistances, the three 6 kilo ohm resistances. So it should become 2 kilo ohms resistance as shown here, and the equivalent circuit is this one. And this 6 kilo ohm resistance is from this one, and this 6 kilo ohm resistance is from this one. So now since that you have the equivalent three resistances, which is 2 kilo ohm, now you can find out the V naught contribution by multiplying the 2 kilo ohms to the 6 milliampere current. And since the current is entering the negative terminal, the voltage is negative 12 also. So you can find out the contribution of this current source in two different ways. Finally, you sum up the contribution of all the three sources, which is shown here, and you end up getting minus 10 volt.